Hi, let us talk about more bitwise operators. So the first bitwise operator that we are going to talk about is bitwise not or bitwise complement. As the name suggests, what it does, it takes an input number, considers its binary representation and inverts every bit. What we mean by invert? 0 becomes 1 and 1 becomes 0. So if a binary number is 1, then its binary representation is this. In Java, integers are 32 bits. So these are 31 zeros and then there is a 1. When you do not of x, you get 31 ones and a 0. Now what is the value of it? What is the integer value that you will get on screen? That is something not easy to guess, because if 31 ones and then a 0. To guess the output, we must know how signed numbers are stored in Java. Java integers have this range from minus 2 raised to the power 31 to 2 raised to the power 31 minus 1. In Java, positive numbers are simply stored by doing decimal to binary conversion. For example, if you have a number 3 plus 3, it's going to be stored as 1 1 at the end and then 30 zeros. That's it. But negative numbers are stored in 2's complement form. What do we mean by 2's complement form and how these positive and negatives are identified? So the simple rule is the leading bit, the leftmost bit, if it is 0, then it's a positive number, and if it's a 1, then it's a negative number. That's the first rule. So this number is positive, but after doing the complement, you get a negative number. Now 2's complement representation is, if you are given a negative number minus x, its 2's complement representation is 2 raised to the power 32 minus x. You simply get this number, do simple decimal to binary conversion of this number. Whatever binary representation you get, that's the binary representation of minus x. That's how negative numbers are represented in Java. So if you see this number, what is the value of this number? This number has value 2 raised to the power 32 minus 1 minus 1. How did I get this number? Please note that 2 raised to the power 32 minus 1 is 32 ones. Right? You can do some examples. For example, 2 raised to the power 3 minus 1 is 3 ones. 8 minus 1, 7, and you have 3 ones. So 2 raised to the power 32 minus 1 is all 32 ones. And when you subtract 1 from it, you get this number, right? And if you use this formula, you can guess the output of this program. So this is basically representation of 2 raised to the power 32 minus 2, right? So which negative number this represents? It definitely represents a negative number because the leading number bit is 1. But which negative number? That we can figure out by comparing these two expressions. So x is actually minus 2. So output that we get out of this program is minus 2. Let's do an exercise now. Let's try to guess the output for this program. I've changed x from 1 to 5. I've written the result of not x. I've just simply written the binary representation. You need to guess the decimal value of this. What will you get as an output on the screen? So you can again use the same logic. Minus x has representation 2 raised to the power 32 minus x. And what is this number? Please note that 2 raised to the power 32 minus 1 means all ones. And what have we subtracted from all ones? We have subtracted 5 from it, right? So this represents a number 2 raised to the power 32 minus 1 minus 5. This minus 5. So what is this? 2 raised to the power 32 minus x or minus 6. So what is x? X is actually minus 6. So you will get minus 6 on the screen. This NOT operator is represented by tilde operator. It's a key in your keyboard below the escape button, just below the escape button. You can use that key to type this operator. And once you apply this operator, all the bits are inverted and you get negative results for positives and you get positive results from negative because the leading bit will also invert. So if you have a positive number, your leading bit will be 0, and if you do an inversion, you will get a negative number. And if you do an inversion of this, you will get a positive number. That's how this operator works. It simply inverts all the bits. Let us now talk about left shift operator. Left shift operator is a binary operator. It takes a number whose binary representation is to be shifted and takes another number that tells how many times we need to shift the binary representation. After shifting the binary representation, whatever new binary representation you get, it returns the corresponding integer value. So if you have x equal to 3 and if you left shift x by 1, so when we say x double angular brackets 1, it means we need to shift binary representation of x by 1. So this is binary representation of x. We have x equal to 3. So we have 30 zeros and then 2 ones. Now if we left shifted by 1, what happens? These bits, all bits, they move here. Right? And your leading 0 is ignored. It's gone, whatever it was. And then a 0 is added at the end. That's how left shift operator works. Right? So what is the value of this? 1, 2, 4. 2 and 4, 6. So the first output that we are going to get here is 6. X left shift 1. When you left shift by 2, these 2 bits are ignored. These remaining 30 bits are moved toward the left side and 2 new trailing zeros are added. So that's your new number. What is the value of this number? 1, 2, 4, 8. 4 and 8, 12. Let us see what is the result of x left shift 4. When you left shift by 4, your 4 leading bits are ignored. Remaining 28 bits are moved ahead and 4 zeros are added at the end. So what is the decimal value of this? 1, 2, 4, 8, 16, 32. 16 plus 32 is 48. So you will get 48 as an output. One interesting thing is, if you left shift this number 3 by 30, what will happen? Your first 30 bits, which are 0 bits, they'll be ignored. And then these 1, 1 will be moved to the beginning. And then 30 zeros will be added at the end. So you will get a number something like 1 and then 30 zeros. If you do shift 3 by 30, that's the result of this, right? If you shift x by 30. And this is some negative number. So you may get negative number if your leading ones, they become the first bit. If one of those leading ones, they become the first bit. So a positive number may convert into negative. Let us do one last example of left shift operator. We have x equal to -1 and we want to guess what is the output of x left shift 1. So negative numbers are represented as 2 raised to the power 32 minus x. So -1 will be represented as 2 raised to the power 32 minus 1, which means all 32 ones. That's how -1 is represented in machine in 2's complement form. Now if you left shifted by 1, what will happen? You will have this bit ignored and these 31 bits will move here. Right? They'll be moved here. Now you will have 31 bits and then you will have a 0 at the end, right? So these 31 bits are moved here and then you have a 0 and this 1 is ignored. You still have a 1 on the left side. So it's still a negative number. Now what is the value of this negative number? You can notice it is simply 2 raised to the power 32 minus 1 minus 1. We only have subtracted 1 from it. So this represents a number whose value is 2 because it's representation of number 2 raised to the power 32 minus 2. So when you left shift -1 by 1, you get the output as -2. The output of this program is -2. In general, for small numbers, whether they are negative or positive, we can say that left shift operator works as multiplication with 2. You remember, right? When we left shifted 3 by 1, we got the output as 2. When we left shifted 3 by 2, we got the output as 12. When we left shifted by 4, we got 24, which is 3 into 2 raised to the power 4. Right? Same happens for negative numbers. When you left shifted minus 1 by 1, you got minus 2. But if it is a large number, then your leading bits might mix up with the sign bit, or some of the leading bits might be ignored. So in those cases, you do not get exact multiplication of 2, but for small numbers, if you left shift a number x by y, your result is x into 2 raised to the power y.